Hello, friend. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. Have you ever looked up at the sky and felt small? Not in a frightening way, but in a way that makes everything else seem quieter. The noise of the day fades. The weight of worry feels lighter. And for a moment, you're just there beneath a ceiling made of light and time. Tonight we're going to drift together into that darkness. Not the kind that frightens, but the kind that remembers. The kind that holds stories older than words, written in points of light that traveled unimaginable distances just to meet your eyes. Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly. And ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's drift. Tonight we'll wander softly into the stories written in darkness, the hidden life of the night sky. A canvas painted not with ink or pigment, but with photons that have been traveling for millions of years, carrying messages from places so distant that time itself begins to lose meaning. You don't need to understand everything. Just rest and let curiosity do the listening. The night sky is the oldest book humanity has ever read, long before we carved symbols into stone, before we spoke. In structured language, we looked up, and in that looking we found meaning. We found direction. We found something that felt almost like belonging. Scientists suggest that our ancestors Homo sapiens walking the African savanna some 300,000 years ago would have seen a night sky more brilliant than anything most of us will ever witness. No city lights, no electric glow bleeding into the atmosphere, just pure unfiltered darkness punctuated by thousands upon thousands of stars. Research shows that in truly dark conditions, away from artificial light, the human eye can perceive roughly 4,500 individual stars. But most of us today, we see fewer than 100. Some studies indicate that nearly 80% of people in North America now live under light-polluted skies. We've traded darkness for convenience, and in doing so, we've lost something ancient. But darkness isn't absence. It's a canvas, a mirror, a space where light becomes visible. Think about it. You can't see a star in daylight, not because the star isn't there, it's shining just as brightly as it does at night. But the sun's light floods our atmosphere, scattering blue wavelengths in every direction, painting the sky in shades that overwhelm the distant pinpricks of starlight. It's only when the Earth turns away from the sun, when our corner of the planet rotates into shadow, that we can finally see what was there all along. Darkness doesn't create the stars, it reveals them. The ancient Babylonians understood this in their own way. Around 1800 BCE, they began recording the movements of celestial bodies on clay tablets, one of the first systematic attempts to map the sky. They tracked Venus, Mars, Jupiter. They noticed patterns, repetitions. They realized that the heavens weren't random, but predictable. And if the heavens were predictable, perhaps the future was too. They didn't have telescopes. They didn't understand gravity or orbital mechanics. But they had something equally powerful: patience. Night after night, year after year, they watched. They waited. They remembered. And slowly the sky began to speak. The Egyptians too were listeners of the night. They noticed that just before the annual flooding of the Nile, an event crucial to their survival, a particular star would rise just before dawn. They called it Sopdet. We call it Sirius, the brightest star in our night sky. Sirius rises in what astronomers now call a heliacal rising, the first appearance of a star on the eastern horizon just before sunrise, after a period of being hidden by the sun's glare. For the Egyptians, this wasn't just astronomy. It was a message, a promise. The river would flood, the fields would be fertile, life would continue. And they were right. Not because Sirius caused the flooding, of course, but because the orbital mechanics of Earth and the physics of our solar system created a pattern reliable enough to stake an entire civilization on. That's the thing about the night sky. It doesn't lie. It doesn't change its story based on who's listening. A photon that left Sirius 8.6 years ago travels in a straight line through the vacuum of space, crosses the void, enters Earth's atmosphere, passes through your cornea, strikes your retina, and triggers an electrical signal that your brain interprets as light. That journey is the same whether you're a farmer in ancient Egypt or someone lying in bed tonight, too tired to sleep, staring through a window at a single bright point in the darkness. The Polynesians took this relationship with the night sky even further. They became some of the greatest navigators in human history, not with compasses or GPS, but with what they called wayfinding, a practice so precise, so intuitive that they could sail across thousands of miles of open ocean and arrive exactly where they intended. How? By reading the stars. They used something called a star compass, not a physical object, but a mental map. The horizon was divided into directional houses, each associated with specific stars as they rose and set. Navigators memorized the positions of over 200 stars. They knew which stars rose in the east, which set in the west, and how those positions shifted throughout the year. But it wasn't just stars. They read the swells of the ocean, the flight patterns of birds, the color of clouds. The entire world became text. And the night sky. That was the most reliable paragraph. Research conducted in the 1970s by the Polynesian Voyaging Society demonstrated that these traditional methods still work. A crew sailed a double-hulled canoe called Hokulea from Hawaii to Tahiti, a distance of about 400 miles using only traditional wayfinding techniques. No modern instruments, no charts. Just stars, ocean, and memory. And they arrived. That's not luck, that's knowledge. Knowledge encoded not in books, but in practice. In the relationship between a human mind and the night sky. The Maya in what is now Mexico and Central America built entire cities aligned with celestial events. Their pyramids weren't just monuments, they were calendars, observatories, tools for tracking time on scales both human and cosmic. At Chichen Itza during the spring and autumn, equinoxes, the setting sun creates a shadow along the steps of the pyramid known as El Castillo. The shadow forms the shape of a serpent slithering down the side of the structure. This wasn't accident, it was design. A visual representation of celestial mechanics readable by anyone who stood in the right place at the right time. The Maya developed one of the most accurate calendar systems in the ancient world. They tracked the cycles of Venus with such precision that their measurements differ from modern calculations by only about 2 hours over a period of 500 years. 2 hours over 5 centuries. Without telescopes, without computers, just eyes and darkness and the patience to watch. But here's the thing that's easy to forget. The patterns we see in the night sky aren't really there, not in the way we think. When we look at the constellation Orion, we see a hunter, a belt, a sword. But the stars that make up Orion aren't close to each other. Betelgeuse, the red supergiant marking Orion's shoulder, is about 550 light-years away. Rigel, the blue supergiant at the opposite corner, is roughly 860 light-years distant. And Bellatrix, another bright star in the constellation, sits around 250 light-years from Earth. They're not neighbors. They don't orbit each other. They exist in completely different regions of space. The only reason they form a pattern is because of where we're standing. From Earth, they line up. But from anywhere else in the galaxy, Orion would look completely different, or wouldn't exist at all. The constellations aren't maps of the stars. They're maps of us, of the way our brains search for meaning, for connection, for something familiar in the chaos. Neuroscience research shows that the human brain is exceptionally good at pattern recognition, sometimes too good. We see faces in clouds, animals in ink blots, and hunters in random distributions of distant suns. This tendency is called pareidolia, and it's not a bug, it's a feature. For most of human history, being able to quickly identify patterns, a predator in the brush, a face in the darkness, was a survival skill. Those who saw patterns lived long enough to pass on their genes. Those who didn't, well, they became part of someone else's pattern. So, when ancient humans looked up and saw lions, bears, scorpions, and gods, they weren't being primitive or superstitious. They were being human. They were using the only tool they had, a brain wired for survival, to make sense of something vast and unknowable. And in doing so, they created something beautiful. Because here's the truth, the stars don't care what we call them. They don't know they're part of a hunter or a bull or a dragon. They're just burning balls of hydrogen and helium, fusing atoms in their cores, releasing energy that travels across light years of emptiness until sometimes it reaches a small blue planet where creatures made of stardust have learned to look up and wonder. But we care. We've always cared. The oldest known star chart dates back to around 32,500 years ago, carved into mammoth ivory in what is now Germany. It shows the constellation we now call Orion, 32,000 years. And we're still looking at the same pattern. The stars in that constellation have barely moved in all that time. Oh, they have moved. Stars aren't static. They're traveling through space at speeds that would seem incomprehensible if we could perceive them. But they're so far away that from our perspective, they might as well be frozen. This is what astronomers call proper motion, the apparent change in position of a star against the background of more distant objects. For most stars visible to the naked eye, proper motion is measured in milliarc seconds per year. A milliarc second is 1 with 3,600 1,000th of a degree. In other words, slow. Unimaginably slow from a human perspective. But over tens of thousands of years, over hundreds of thousands, the constellations will change. The sky our descendants see will not be the sky we see now. And the sky we see now is not quite the same sky our ancestors carved into ivory all those millennia ago. The universe is moving. We're moving. Everything is moving. But for now, in this moment, the stars are where they've always been, waiting. Watching, telling their stories to anyone patient enough to listen. And tonight, we're listening. So, when you look up at the night sky, remember you're not just seeing light. You're seeing time. You're seeing distance. You're seeing the past, present, and future all collapsed into a single moment of perception. You're seeing a story that began before you were born and will continue long after you're gone. And somehow, in the midst of all that vastness, all that time, all that impossible distance, you're here, right now. Looking up, that's not nothing. That's everything. The ancient Greeks had a word, anamnesis. It means something like unforgetting. The idea that learning isn't about discovering something new, but about remembering something you've always known. Maybe that's what happens when we look at the stars. We're not learning. We're remembering. Remembering that we're part of something larger. Remembering that the same atoms that make up our bodies were once inside the cores of stars that lived and died billions of years ago. Remembering that we are quite literally children of the cosmos, made of light, made of time, made of the same material as the darkness and the stars and the endless space between. The night sky doesn't just hold stories, it is a story, and you're part of it. So rest now. Let the darkness hold you. Let the stars breathe their ancient light into your thoughts. There's so much more to see, so much more to feel, and we've only just begun. The light that reaches us from distant stars carries more than just brightness. It carries information coded in wavelengths and frequencies, in patterns that telescopes and spectrometers can decode. Every photon is a message, and some of those messages have been traveling for so long that the stars that sent them no longer exist. Every photon that touches your eye tonight has been traveling, some for years, some for centuries, some for millions of years. And when they finally arrive, they don't just bring light, they bring time itself. The stars we see aren't where they appear to be. They're echoes, memories, light from places that may no longer exist, traveling across distances so vast that by the time it reaches us, the universe has already moved on. But long before we understood any of this, we were reading the sky, not with equations or telescopes, but with something deeper, with need, with wonder, with the kind of attention that only comes when your survival depends on it. The first astronomers weren't scientists, they were survivors. Around 30,000 years ago, someone stood beneath a night sky in what is now Europe and carved marks into bone. Not decorations, not random scratches, but a record, a tally. Research suggests these marks tracked lunar phases, the waxing and waxing of the moon over months. Why would someone do this? Why carve the moon's cycle into bone when there were predators to avoid and food to find and endless immediate concerns? Because patterns meant survival. Knowing when the moon would be full meant knowing when you could hunt at night. Knowing the seasons meant knowing when animals would migrate, when plants would fruit, when rivers would flood or freeze. The sky wasn't something to admire, it was something to read. A text written in light and motion and repeating cycles that, if you paid close enough attention, could tell you when to act and when to wait. The Babylonians took this further than almost anyone. Around 1800 BCE in the region between the Tigris and Euphrates rivers, scribes began recording celestial observations on clay tablets. Not occasionally, not when something unusual happened, but systematically, night after night, year after year. They tracked Venus, the brightest object in the sky, after the sun and moon. They noticed it appeared as both a morning star and an evening star, not realizing these were the same object. They recorded its positions, its brightest appearances, its disappearances behind the sun. And then they did something remarkable. They found patterns. Venus, they discovered, moved in a cycle. It would appear in the evening sky for about 263 days, disappear for about 50 days, reappear in the morning sky for another 263 days, then vanish again for about 8 days before starting the cycle over. The total cycle took about 584 days. They didn't know Venus was a planet. They didn't understand orbits or gravity or the heliocentric model of the solar system, but they knew the pattern, and that was enough. Some historians suggest the Babylonians could predict Venus's position up to a year in advance with reasonable accuracy. Not because they understood the physics, but because they trusted the pattern. They believed the universe repeated itself, and in many ways, they were right. This is one of the earliest examples of what we might call predictive astronomy. Not explaining why something happens, but knowing that it will happen. Observation without theory. Pattern without mechanism, and it worked. The ancient Egyptians had their own relationship with the sky, one tied directly to the rhythm of their entire civilization. The Nile River flooded every year, depositing rich, dark soil across the floodplain soil that made agriculture possible in an otherwise desert landscape. But when would the flood come too early, and you'd still have crops in the ground? Too late, and you might miss the planting season. The timing mattered, so they watched the sky. Just before the annual flooding, usually in mid-July, a particular star would rise in the east just before dawn, a phenomenon called a heliacal rising. The star was Sirius, the brightest in the night sky, part of the constellation Canis Major. The Egyptians called it Sopdet. The Greeks later called it Sirios, meaning scorching or glowing. We know it as Sirius the dog star. And when Sirius rose, the Nile would flood, not immediately but soon, within days or weeks. This wasn't magic. It was orbital mechanics. Earth's position in its orbit around the sun, combined with the relative position of Sirius, created a reliable correlation. Sirius's heliacal rising coincided with the flooding season not because one caused the other, but because both were part of the same cosmic clockwork. The Egyptians built their entire calendar around this. The appearance of Sirius marked the beginning of the year. The year became 365 days remarkably close to the true length of Earth's orbit, which is about 365.25 days. That quarter-day difference might seem small, but over decades and centuries it adds up. The Egyptian civil calendar slowly drifted out of sync with the actual seasons. They knew this. They tracked it. But for practical purposes, the system worked well enough for over 3,000 years. 3,000 years, using nothing but careful observation and patient record-keeping. But perhaps the most extraordinary astronomical achievement of the ancient world belongs to a group of people who never built pyramids or ziggurats, who left no written records, who had no cities or empires: the Polynesians. They crossed the Pacific Ocean, not once, not accidentally, but repeatedly, deliberately navigating thousands of miles of open water with such precision that they could return to islands barely visible on the horizon. How? By reading everything. The stars, the swells of the ocean, the color of clouds, the flight paths of birds, the taste of the wind. But the stars were the foundation. Polynesian navigators used what's called a star compass, though it's not a physical object. It's a mental framework. Imagine the horizon as a circle divided into directional houses, specific points where certain stars rise and set. Navigators memorized over 200 stars. They knew exactly where each one would appear on the horizon, and they knew how that position changed throughout the year. As one star rose too high to be useful, another would take its place in the same directional house. This wasn't abstract knowledge, it was practical. If you wanted to sail from Tahiti to Hawaii, a distance of about 2,500 miles across empty ocean, you'd aim for the star that rose over Hawaii. You'd keep that star at a certain angle off your bow. When it rose too high, you'd switch to the next star in the sequence. But stars alone aren't enough. The Pacific is too vast. Weather changes, currents shift. You need redundancy. So, Polynesian navigators also read the ocean. Deep ocean swells move in consistent patterns generated by distant storms and trade winds. These swells travel for thousands of miles, crossing the entire Pacific in predictable directions. If you know how to feel them, and skilled navigators could feel the difference between swells, by lying in the hull of the canoe, you can orient yourself even when clouds hide the stars. They read clouds too. Certain types of clouds form over islands, but not over open ocean. A greenish tint to the underside of a cloud might reflect a lagoon. Birds, especially certain species, fly out to sea in the morning and return to land in the evening. If you see birds flying in a consistent direction, at dusk land is that way. Western scholars didn't believe this was possible. Not really, not with the accuracy claimed by the stories. Then, in 1976, a group decided to test it. They built a traditional double-hulled voyaging canoe called Hokulea, Star of Gladness, the Hawaiian name for Arcturus, one of the brightest stars in the northern hemisphere. They recruited Maupiailug, a master navigator from Sadawal, a tiny island in Micronesia, one of the last people alive who still practiced traditional wayfinding. The plan sailed from Hawaii to Tahiti using only traditional methods: no compass, no sextant, no GPS, no charts, just stars, ocean, and memory. It took 33 days. They traveled about 2,400 miles, and they arrived, not approximately, not close enough. They arrived. Maupiailug, navigating by methods passed down through generations, brought the canoe to within sight of Tahiti without ever being lost. The success of Hokulea didn't just prove that ancient navigation techniques worked, it sparked a renaissance of traditional wayfinding across the Pacific. Young people began learning from the few remaining master navigators. Ancient knowledge that was on the verge of disappearing found new life. Because it wasn't primitive, it was sophisticated, just in a way that didn't require writing or instruments. It required something else: intimacy with the world, a kind of attention so complete that the ocean, the sky, and the navigator became part of the same system. The Maya in Mesoamerica brought a different kind of precision to the night sky. They built observatories' actual structures designed for watching celestial events. The most famous is probably El Caracol at Chichen Itza, a circular tower with narrow windows aligned to specific astronomical events. But their genius wasn't just in buildings, it was in mathematics, in record-keeping, in obsession. The Maya tracked Venus with extraordinary care. They knew its cycle, that 584-day pattern the Babylonians had also discovered. But the Maya went further. They recorded Venus's movements over centuries and noticed something subtle: 5 Venus cycles almost exactly equal 8 Earth years. 5 times 584 is 920 days. 8 years is about 922 days. Close but not perfect. Over long periods, this tiny discrepancy adds up. The Maya knew this. They corrected for it. Their calculations for Venus's cycle, refined over generations, differ from modern astronomical measurements by only about 2 hours over a 500-year period. 2 hours in 5 centuries. Without telescopes, without computers, without even a system of fractions, Maya mathematics used whole numbers and a sophisticated place value system based on 20. But they didn't have decimal points or the concept of continuous fractions, the way later European mathematics did. They simply watched, recorded, calculated, refined. Why? Why spend generations perfecting the tracking of a bright dot that moves across the sky? For the Maya, astronomy and time weren't separate from life. They were life. The calendar wasn't just a tool for knowing when to plant crops. It was a sacred text. Time itself was divine, cyclical, layered with meaning. Certain days were auspicious, others were dangerous. The movements of celestial bodies influenced when to wage war, when to perform rituals, when kings should be crowned. To know the sky was to know the will of the gods. To predict celestial events was to glimpse the future. We might call this superstition. But from another perspective, it's something else: taking the universe seriously. Believing that patterns matter, that the cosmos isn't random chaos, but ordered, meaningful, knowable, and in believing that they made it true, not because the stars controlled human fate, but because humans, in seeking to understand the stars, developed mathematics, record-keeping architecture, and systems of thought that shaped civilizations. The ancient Chinese also watched Venus. They called it Taibai, Great White. Like the Maya and Babylonians, they tracked its movements, recorded its appearances and disappearances. But Chinese astronomers did something unusual. They recorded what they called guest stars that appeared suddenly where none had been, before shone brightly for weeks or months, then faded away. In 1054 CE, Chinese astronomers recorded a guest star in the constellation we call Taurus. It was so bright it was visible during the day for 23 days. At night, you could read by its light. Then, over the following months, it slowly dimmed and disappeared. They didn't know what they were watching, but they wrote it down. We know now what they saw: a supernova, a massive star, at least 8 times the mass of our sun, reaching the end of its life and exploding with such violence that for a brief time, it outshone every other star in the galaxy. The remnant of that explosion is still visible today. We call it the Crab Nebula. It's about 6,500 light-years away, meaning the light from the explosion took 6,500 years to reach Earth. So, when Chinese astronomers saw it in 1054, they were watching something that had actually happened around 5450 BCE, long before, writing before cities, before agriculture. But the light took that long to arrive, and when it did, someone was watching. That's what ancient astronomy was paying attention, not understanding necessarily, not explaining, but witnessing. And there's something profound in that, something that goes beyond data and theory. Because when you watch the sky, night after night, year after year, generation after generation, you begin to notice something. You're not separate from it. You're not an observer standing outside the system, taking notes. You're in it. You're part of the pattern. The same gravity that holds planets in orbit pulls on your body. The same atoms that burn inside stars make up your bones. the light that left a distant sun 1,000 years ago, crosses the universe and enters your eye, triggering chemical reactions that let you see. You're not watching the cosmos is watching itself through you. The ancient astronomers didn't have that language. They didn't know about atoms or photons or the electromagnetic spectrum, but maybe in some way they understood it better than we do. Because they didn't separate knowledge from experience. They didn't study the sky, they lived with it. They let it shape their calendars, their myths, their sense of time and place and meaning. The sky wasn't something to figure out. It was something to belong to. And maybe that's what we've lost. Not the data, we have more data than ancient astronomers could have imagined, but the relationship, the intimacy, the sense that when you look up, you're not looking at something distant and abstract, but at something that's looking back, something that holds you, something you're part of. The first astronomers knew this, not intellectually, but in their bones. And maybe just for tonight we can remember it too. The stars are still there, still moving, still carrying their messages across the dark. And if we're patient enough, quiet enough, if we let go of the need to understand and simply watch, we might begin to hear what they're saying. Not in words, not in equations, but in something older, something that doesn't need translation because it speaks in the language we were born knowing. The language of light traveling through darkness, finding eyes that evolve to receive it, minds that evolve to wonder at it. We are, after all, the universe's way of seeing itself. And that's what makes starlight so strange, so quietly impossible. Because the light touching your eyes right now didn't start its journey today, or yesterday, or even in your lifetime. Some of it has been traveling since before you were born, before your parents were born, before humans walked upright or spoke in sentences or wondered what those bright points in the darkness might be. Light moves fast, faster than anything else in the universe. But space is so vast that even at light's incredible speed, most of what we see in the night sky is ancient, not old, ancient. When you look up tonight, you're not seeing the stars as they are. You're seeing them as they were. The night sky is a museum of time, and every point of light is an artifact from a different era. Let's start close to home. The nearest star to Earth besides our sun is Proxima Centauri. It's part of a triple star system called Alpha Centauri, sitting about 4.24 light-years away. A light year isn't a measurement of time exactly, it's a measurement of distance. It's how far light travels in 1 year. And light in a vacuum travels at about 186,282 miles per second. That's roughly 671 million miles per hour. At that speed, light from the sun takes about 8 minutes and 20 seconds to reach Earth. We're 93 million miles away, and light covers that distance faster than you can finish a cup of coffee. But Proxima Centauri is 4.24 light-years away. That's about 25 trillion miles. So when you see Proxima Centauri, and you can't with the naked eye, it's too dim. But if you could, the light entering your eye left that star over 4 years ago. If Proxima Centauri exploded tonight, we wouldn't know for more than 4 years. The star could already be gone, and we'd still see it shining. Still think it was there because the last light it emitted is still traveling toward us. The past isn't behind us, it's above us, written in light. Now let's go a bit farther. Sirius, the brightest star in our night sky, the one the Egyptians watch for signs of the Nile's flooding. Sirius is about 8.6 light-years away. The light you see from Sirius tonight left that star in early 2016. Think about where you were in 2016, what you were doing, who you were. That version of you, that moment in your life, that's when this light began its journey. It's been traveling through the void ever since crossing trillions of miles of empty space until tonight, when it happened to intersect with your eye. Vega, another bright star, is about 25 light-years away. The light from Vega you're seeing now left that star around the year 2000. The turn of the millennium, Y2K, a different world, a different you perhaps. And the light from that moment is only just arriving, but these are still our neighbors. Cosmically speaking, they're in our backyard. Let's go deeper. Betelgeuse, The red supergiant that marks the shoulder of Orion is roughly 550 light-years away. The light from Betelgeuse that reaches Earth tonight left that star around the year 1475. Christopher Columbus was 24 years old. The printing press had just been invented. Leonardo da Vinci was painting his first works. When that light began, its journey no European had ever seen the Americas. The Ottoman Empire was at its height. Joan of Arc had been dead for only 44 years, and the light just kept moving, through wars and empires and the rise and fall of civilizations. Through the Reformation, the Enlightenment, the Industrial Revolution, through 2 world wars, through the invention of the airplane, the computer, the internet. 550 years of human history, and the light just traveled, silently, relentlessly, at 186,282 miles per second. And tonight it arrives. It enters your eye, and for a fraction of a second, you're connected to a star as it existed in 1475. Betelgeuse, by the way, might already be gone. It's a supergiant nearing the end of its life. It could explode as a supernova at any time, astronomically speaking, which means it could happen tomorrow or 100,000 years from now. Scientists suggest that when it does explode, it will be bright enough to see during the day, possibly as bright as the full moon. But if it exploded 500 years ago, we wouldn't know yet. We'd still see it shining, still mark it as one of the brightest stars in Orion. The explosion would still be on its way, light rushing toward Earth, carrying the news of a star's death. Now, let's go farther still. The Andromeda Galaxy. The closest large galaxy to our own Milky Way is about 2.5 million light-years away. You can see it with the naked eye on a dark night. It looks like a faint smudged oval of light. What you're seeing is the combined glow of roughly 1 trillion stars. But you're seeing it as it was 2.5 million years ago. When the light you're seeing tonight left, Andromeda humans didn't exist. Not as we know ourselves. Homo habilis. One of our distant ancestors was just beginning to use stone tools. Our species, Homo sapiens, wouldn't evolve for another 2.2 million years. The light from Andromeda you see tonight has been traveling through space for longer than our entire species has existed. It crossed the void while continents shifted, while ice ages came and went, while life on Earth evolved and adapted and changed in a million ways. And now, tonight it reaches you. Think about that for a moment. You're looking at something that's 2.5 million years old. Not in the sense that the galaxy is old, it's billions of years old, but in the sense that the image you're seeing, the light that's forming that image, is literally ancient. If someone in Andromeda were looking at Earth right now with a powerful enough telescope, they wouldn't see you. They wouldn't see cities or cars or airplanes. They'd see Earth as it was 2.5 million years ago. They'd see a planet with no humans, no agriculture, no written language. Just the long, slow process of evolution unfolding in ways no one could predict. The universe doesn't happen in real time. It happens in light time. And light, for all its speed, still takes time to travel. But here's where it gets even stranger. The farther out we look, the farther back in time we see. Telescopes aren't just magnifying space. They're time machines pointed at the past. The Hubble Space Telescope, launched in 1990, has captured images of galaxies that are over 13 billion light-years away. That's close to the edge of the observable universe. The light from those galaxies has been traveling for 13 billion years, most of the age of the universe itself, which scientists estimate is about 13.8 billion years old. When the light from those distant galaxies began its journey, the universe was young. Stars were just beginning to form. Galaxies were smaller, messier, more chaotic. Earth didn't exist. The sun didn't exist. The Milky Way was still taking shape. And that light just moved for 13 billion years. Through expanding space, through the formation and death of countless stars, through the slow, patient assembly of everything we know, until it reached a telescope orbiting a small blue planet in an ordinary galaxy, and humans, creatures made of stardust, who evolved to look up and wonder, captured it. studied it, tried to understand what it meant. We're not just seeing distant objects, we're seeing the history of the universe, written in light, delivered one photon at a time. But light doesn't just carry images, it carries information. Hidden in the wavelength, the frequency, the spectrum of light, there's data, stories, clues about what the universe is made of and how it works. When astronomers study starlight, they don't just look at how bright it is. They split it into its component colors using an instrument called a spectrograph. What they see is a spectrum, a rainbow of light, but not a smooth, continuous rainbow. There are gaps, dark lines where specific colors are missing. These are called absorption lines, and they appear because atoms in the star's atmosphere absorb certain wavelengths of light. Every element absorbs specific wavelengths. Hydrogen absorbs one pattern, helium absorbs another. Carbon, oxygen, iron, each has its own unique fingerprint. By studying the spectrum of a star, astronomers can determine what it's made of. Not by going there, not by collecting samples, just by looking at the light. This technique is called spectroscopy, and it's one of the most powerful tools in astronomy. It's how we know that the sun is mostly hydrogen and helium. It's how we know that distant stars have iron, carbon, and oxygen, the same elements that make up your body. It's how we know the universe is made of the same stuff everywhere. The atoms here are the same as the atoms billions of light years away. The laws of physics that govern Earth also govern the farthest galaxies we can see. Light tells us this. Light carries the proof. But light also tells us something else, something even stranger: the universe is expanding. And we know this because of light. In the 1920s, astronomer Edwin Hubble, yes, the telescope is named after him, studied the spectra of distant galaxies and noticed something odd. The absorption lines were shifted toward the red end of the spectrum, not by a lot, but measurably. This is called redshift, and it happens because of something called the Doppler effect. You've probably experienced the Doppler effect with sound. When an ambulance drives toward you, its siren sounds higher pitched. When it drives away, the pitch drops. That's because the sound waves are compressed as the source moves toward you and stretched as it moves away. Light does the same thing. If a star or galaxy is moving away from us, its light gets stretched, shifting toward the red end of the spectrum. If it's moving toward us, the light gets compressed, shifting toward blue. Hubble noticed that almost every galaxy he looked at was redshifted. They were all moving away from us. And not just that, the farther away a galaxy was, the faster it was moving. This didn't mean we were at the center of some cosmic expansion. It meant space itself was expanding. Every point in space is moving away from every other point. The universe is stretching, and we know this because light told us. Light carried the message across billions of light years of space, encoded in wavelengths and frequencies, waiting for someone to figure out how to read it. Photons are messengers, tiny massless particles of light that carry information from one part of the universe to another. They don't decay. They don't slow down. They just move at the speed of light until they hit something. Most photons never hit anything. They travel through the universe forever, crossing voids so vast that they might never encounter another particle. They're orphans of light, wandering through the dark, carrying messages no one will ever receive. But some photons, a precious few, make it to Earth. They travel across unimaginable distances through gas clouds and gravitational fields, and the expanding fabric of space itself. And then by sheer chance, they enter a telescope. Or an eye. Your eye. Right now. Every time you look at a star, billions of photons are entering your eye. They strike the retina at the back of your eye, where specialized cells called rods and cones absorb them. That absorption triggers a chemical reaction, which sends an electrical signal through your optic nerve to your brain. Your brain interprets that signal as light, as a star, as beauty. But what you're really experiencing is the end of a journey that might have begun millions of years ago in the core of a star. You'll never visit in a part of the universe you'll never reach. And yet, for a moment, you're connected. Light bridges the gap. It crosses the void. It carries the past to the present, the distant to the near, the star to the eye. Light doesn't just travel, it connects. There's a photon that left Betelgeuse 550 years ago. It's been traveling ever since, and maybe tonight it will enter your eye. Maybe you'll be the one who receives that particular messenger, that particular fragment of a star's ancient light. You'll never know which photon it is. You can't pick one out from the billions, but it doesn't matter, because the light is real, the connection is real. And when you look up tonight, you're not just seeing stars. You're seeing their history, their long, patient journey through the dark. You're seeing time itself frozen in light, delivered across the cosmos to a creature who evolved to wonder at it. That's not nothing. That's everything. The universe speaks in light. It writes its stories in photons and wavelengths and spectra. And if we're quiet enough, if we pay attention, we can read them. Not all of them, not even most of them, but enough. Enough to know we're part of something larger, something older, something that connects us to the farthest reaches of space and time. The light is still traveling. New photons are leaving stars right now, beginning journeys that might take centuries or millennia or millions of years. Some of them will reach Earth long after we're gone. Future eyes will see them. Future minds will wonder at them. And maybe they'll feel what we feel. That strange, quiet awe that comes from knowing you're seeing something that traveled so far for so long just to reach you. Light doesn't care who sees it. It doesn't choose its destination. It just moves, relentlessly, patiently, carrying its message through the void. And sometimes when the universe aligns just right, that message finds its way to someone willing to receive it. Someone standing beneath a night sky, looking up, feeling small and vast all at once. But light isn't the only language the night sky speaks. There are colors hidden in the darkness, colors we can't see, wavelengths beyond the limits of human vision. And those invisible hues tell stories our eyes were never designed to read. Those invisible wavelengths, those colors beyond color, are everywhere. The night sky isn't just black and white and the pale glow of distant stars. It's ablaze with light we can't see, frequencies our eyes weren't built to detect, a hidden world of radiation that tells stories our vision alone could never read. The darkness isn't empty, it's full, fuller than we ever imagined. And the strange thing is, we're blind to most of it. Human eyes are remarkable organs. They can detect a single photon under the right conditions. They can distinguish millions of different shades of color. They can adapt to darkness so well that after about 30 minutes in the dark, your sensitivity to light increases by up to 100,000 times. But for all their sophistication, human eyes are limited. We see what's called visible light electromagnetic radiation, with wavelengths between about 380 and 700 nanometers. That's it. That narrow slice of the spectrum is our entire visual world. A nanometer is 1/1,000,000th of a meter. The width of a human hair is about 80,000 nanometers. So we're talking about incredibly tiny wavelengths. And the visible spectrum, the rainbow of colors from violet to red, spans just 320 nanometers. Below violet, there's ultraviolet light. Wavelengths shorter than 380 nanometers. We can't see it, but it's there. The sun radiates enormous amounts of UV light. It's what causes sunburns, what triggers vitamin D production in your skin, what makes certain materials fluoresce under black lights. Above red, there's infrared. Wavelengths longer than 700 nanometers. Infrared is heat radiation. Warm objects, including your body, emit infrared light. Night vision goggles detect infrared. Thermal cameras see the world in infrared. But your eyes, they're blind to it. And beyond infrared and ultraviolet, the spectrum stretches infinitely in both directions. Radio waves with wavelengths measured in meters, microwaves, X-rays, gamma rays. All of it is light. All of it is electromagnetic radiation, traveling at the speed of light, carrying information. But we see only a sliver, a thin band in the middle of an infinite spectrum. Why? Why are we limited to this narrow-range evolution? Our eyes evolved under the light of the sun, and the sun emits most of its energy in the visible spectrum. It makes sense that our vision would adapt to the kind of light that's most abundant in our environment. Seeing ultraviolet or infrared might have been useful, but it wasn't useful enough to be selected for. The visible spectrum was enough for survival, so we see what we need to see, and the rest of the universe remains invisible. But here's where astronomy becomes almost magical. We've built instruments that can see what we can't. Telescopes that detect ultraviolet and infrared and radio waves and X-rays. We've extended our vision beyond the limits of biology. And when we look at the night sky through these instruments, we see a completely different universe. Take the Crab Nebula, for example, the remnant of that supernova Chinese astronomers witnessed in 1054. In visible light, it looks like a pale, cloudy structure. Beautiful, but relatively subtle. But look at it in X-rays and it blazes. The core of the nebula contains a pulsar, a rapidly spinning neutron star that emits beams of X-ray radiation like a cosmic lighthouse. That pulsar spins about 30 times per second, and with each rotation it releases a burst of high-energy radiation. None of this is visible to the naked eye, but it's real. It's happening. The universe is performing this incredible light show, and we'd miss it entirely if we relied only on what evolution gave us, or consider the center of our own galaxy, the Milky Way. If you look toward the constellation Sagittarius on a dark night, you can see a dense band of stars and dark dust clouds. It's stunning, but you're not seeing the center. Not really. The galactic center is hidden behind thick clouds of interstellar dust. Dust particles scatter visible light, making it impossible to see through. It's like trying to see through fog. The light just doesn't make it to us, but infrared light. Infrared passes through dust much more easily. Longer wavelengths aren't scattered as much by small particles. So, if you look at the galactic center in infrared, the dust becomes nearly transparent. You can see through it, and what you find is astonishing. Massive star-forming regions, dense clusters of young hot stars, and at the very center, hidden behind everything else, a supermassive black hole called Sagittarius A, with a mass about 4 million times that of the Sun. We couldn't see any of this in visible light. We had to learn to see in infrared. NASA's James Webb Space Telescope, launched in 2021, is designed primarily to observe in infrared. It's stationed about 1 million miles from Earth, in a position where the Sun, Earth, and Moon are all in the same direction, so their heat and light don't interfere with observations. Why infrared? Because infrared lets us see farther into the past. Remember, the universe is expanding. As space expands, light traveling through it gets stretched. This is the redshift we talked about earlier. Light that started as visible or ultraviolet billions of years ago has been stretched into infrared by the time it reaches us. So, if you want to see the earliest galaxies that formed when the universe was young, you need to look in infrared. The James Webb Space Telescope has captured images of galaxies that formed just a few 100 million years after the Big Bang. Galaxies so distant, so ancient, that their light has been traveling for over 13 billion years. None of these galaxies are visible to the human eye. They exist only in infrared at wavelengths our eyes can't detect. But they're there. And they're teaching us about the history of the universe, about how stars and galaxies form, about what the cosmos looked like in its infancy. We've learned to see in colors we can't see. And in doing so, we've discovered a universe far stranger and more complex than visible light alone could ever reveal. But it's not just about astronomy. Other species on Earth can see beyond the human spectrum. And when you realize this, it changes how you think about perception, about reality, about what it means to see something. Bees, for example, can see ultraviolet light. Flowers that look plain white or yellow to us are covered in UV patterns invisible to humans but clear as day to a bee. These patterns guide the bee to nectar, like runway lights guiding a plane. The flower is advertising, the bee is navigating, and it's all happening in a color we can't perceive. If you could see in ultraviolet, the world would look radically different. Some birds also see UV light, and research suggests it helps them identify ripe fruit track prey and even choose mates. Certain species of birds have plumage that looks identical to us, but displays brilliant UV patterns visible to other birds. They are seeing colors we don't have names for, colors that don't exist in human experience. Snakes, at least some species like pit vipers and pythons, can sense infrared radiation. They have specialized organs called pit organs, located between their eyes and nostrils that detect heat. This lets them see warm-blooded prey in complete darkness. To a pit viper, a mouse glows. It radiates infrared light, a heat signature that stands out against the cooler background. The snake doesn't need visible light. It hunts in a spectrum humans can't access. Even some insects can detect polarized light waves that vibrate in a particular direction. Many insects use polarized light patterns in the sky to navigate even when the sun is hidden by clouds. It's like having a built-in compass that works in any weather. The point is, this reality isn't limited to what we can see. Our eyes give us one version of the world. But it's not the only version. It's not even the most complete version. It's just the version we evolved to perceive. And when we build instruments that extend our senses when we look at the universe in wavelengths we can't naturally see, we discover that we've been missing most of the story. The famous pillars of creation, one of the most iconic images ever taken by the Hubble Space Telescope, shows towering columns of gas and dust in the Eagle Nebula, about 6,500 light-years away. The image is breathtaking, dark pillars silhouetted against glowing gas studded with newborn stars. But that image isn't what you'd see if you flew to the Eagle Nebula and looked with your eyes. It's a composite. Hubble captured the nebula in multiple wavelengths. Visible light, yes, but also hydrogen alpha emission, ionized sulfur, ionized oxygen. Each wavelength was assigned a color, and the images were layered together. The result is stunning. But it's not real in the way we usually think of photographs as real. It's enhanced, translated, made visible. Scientists do this all the time. They take data from wavelengths we can't see and map it onto colors we can. Infrared becomes red. X-rays become blue. It's not deceptive, it's practical. It's the only way to share what the instruments are detecting. But it also means that the images we see of nebulae galaxies and distant stars are interpretations. They're accurate based on real data, but they're filtered through human perception. We're taking the invisible and making it visible, translating the language of the universe into something our eyes can process. And that's not a limitation, that's ingenuity. That's humans doing what we do best, adapting, extending, reaching beyond our natural limits to understand more. The universe doesn't care what we can see. It doesn't cater to human biology. It simply is. Radiating across the entire electromagnetic spectrum, from the longest radio waves to the shortest gamma rays, carrying information, telling stories, performing light shows that happen whether or not anyone is watching. But we're watching now, with instruments that see in ultraviolet and infrared and X-rays, with telescopes that orbit above the atmosphere where Earth's air doesn't block the light, with detectors sensitive to wavelengths that would pass right through our eyes without triggering a single response. We've become more than what evolution made us. We've extended our senses. We've learned to see in colors that don't exist in human experience. And what we've found is extraordinary. The night sky viewed in radio waves looks nothing like the night sky in visible light. Radio telescopes detect emissions from objects that are invisible or dim in optical wavelengths, pulsars, quasars, the remnants of supernovae, the faint glow of hydrogen gas drifting between stars. One of the most famous radio sources in the sky is called Cygnus A, located in the constellation Cygnus. In visible light, it looks like a faint, unremarkable galaxy. But in radio wavelengths, it's one of the brightest objects in the sky. It emits enormous jets of radio waves powered by a supermassive black hole at the galaxy's center. Those jets extend for hundreds of thousands of light years, far beyond the visible galaxy itself. We never would have discovered Cygnus A if we'd limited ourselves to visible light. We never would have known that galaxies could produce jets, that black holes could launch material at relativistic speeds, that the universe was full of invisible structures powered by gravity and magnetism and unimaginable energies. The universe is larger, stranger, and more active than it appears, but only if you know how to look. X-ray astronomy has revealed another hidden layer of the cosmos. X-rays are high-energy photons usually produced by extremely hot or violent events. Earth's atmosphere blocks most X-rays, which is good for us. X-rays can damage living tissue, but it means X-ray telescopes have to be in space. NASA's Chandra X-ray Observatory, launched in 1999, has captured X-ray images of black holes, neutron stars, supernova remnants, and galaxy clusters. In X-rays, the universe is a violent, energetic place. Stars explode. Black holes devour matter. Gas clouds heat to millions of degrees and emit radiation that our eyes could never detect. But it's happening. All of it. Right now. In wavelengths we can't see. The sun itself is a different creature when viewed in different wavelengths. In visible light, it's a smooth, bright sphere. But look at it in ultraviolet or X-rays and you see something much more dynamic. Coronal loops, giant arcs of plasma following magnetic field lines. Solar flares, sudden bursts of energy that release the equivalent of billions of nuclear bombs. Dark sunspots and bright, active regions that change day by day. The sun isn't calm, it's roiling, churning, erupting, but we don't see this in visible light. We had to learn to see in other wavelengths to understand what the sun really is. And this raises a strange question. If we can only see a narrow slice of reality, what else are we missing? Not just in the sky, but here on Earth, right now. There are radio waves passing through your body at this moment, from cell towers, from satellites, from distant stars. You can't feel them, you can't see them, but they're real. Electromagnetic radiation carrying information, moving at the speed of light. There's infrared radiation radiating from your skin, from the walls around you, from every warm object nearby. If someone were looking at you with an infrared camera, they'd see you glowing a heat signature distinct from your surroundings. There's ultraviolet light from the sun, even on cloudy days passing through windows, striking surfaces, triggering chemical reactions you'll never see. Reality is so much more than what reaches our eyes. In the night sky, the darkness we look up into is full of light and energy and information radiating across wavelengths we evolved to ignore because we didn't need them to survive. But now we do. Now, if we want to understand the universe, we need to see beyond the limits of human vision. We need to embrace the colors we can't see and learn the stories they tell. Because the universe speaks in every wavelength. It writes its history in gamma rays and radio waves and everything in between. And if we only listen to the narrow band we call visible light, we're missing most of the conversation. The invisible universe is still the universe, and it's speaking to us. We just had to learn its language. The night sky is more than what meets the eye. It's more than what any eye could ever see. It's a symphony played in frequencies most creatures can't hear. A painting rendered in colors that don't exist in human experience. And yet, somehow, we've learned to translate it, to see it, to understand it. That's the real miracle. Not that the universe is full of invisible light that's just physics. The miracle is that we limit it as we are figured out how to extend our senses, how to build instruments that see what we can't, how to take data from wavelengths beyond our perception and turn it into knowledge. We're creatures of visible light living in a universe that radiates in every direction at every frequency. And we've learned to see it all. The stars aren't just points of light anymore. They're beacons broadcasting across the spectrum. And with the right tools, we can finally hear what they've been saying all along. But the stars don't just shine, they move. And long before we had instruments to measure invisible light, we learned to track their motion, to use their predictable paths as guides across oceans and deserts, as calendars carved into the turning sky. Those carved calendars in the sky, those predictable patterns of light and motion, became something more than markers of time. They became directions, coordinates, a map written in fire and distance, readable by anyone who knew how to trace the lines between stars and make meaning from their movement. The night sky doesn't just tell you when, it tells you where. And for thousands of years, before GPS satellites and digital compasses, before paper maps and magnetic needles, the stars were the only reliable guide across a world that seemed infinite and unknowable. Navigation by starlight isn't instinct, it's learned. It's passed down through generations, refined through trial and error, encoded in stories and songs and careful observation. It's humans doing what we do best, finding patterns in chaos and using them to survive. But here's what's remarkable. We weren't the only ones. Birds do it. Sea turtles do it. Even dung beetles' research suggests navigate using the Milky Way. The night sky is a map that doesn't belong to humans alone. It belongs to any creature with eyes capable of seeing it and a brain capable of remembering. Let's start with the most famous navigational star in the Northern Hemisphere, Polaris, the North Star. Polaris sits almost directly above Earth's North Pole. As Earth rotates, the entire sky seems to turn around Polaris. Every other star traces a circle through the night, rising in the east and setting in the west. But Polaris barely moves. It stays fixed, a constant point in the turning sky. If you're in the Northern Hemisphere and you can find Polaris, you know which way is north. Always. Regardless of the time of night, the season, the weather. Polaris doesn't lie. Sailors knew this. For centuries, anyone venturing out of sight of land learned to find Polaris. The easiest method is to use the Big Dipper, a constellation most people in the Northern Hemisphere can recognize. The two stars at the front edge of the Dipper's cup point almost directly at Polaris. Follow that line about 5 times the distance between those two stars, and you'll find it. Once you have north, you have everything. You can orient yourself. You can set a course. You can navigate. But there's a catch. Polaris is only useful in the Northern Hemisphere. The farther south you travel, the lower Polaris appears on the horizon. Once you cross the equator, it disappears entirely, hidden below the curve of the Earth. Southern Hemisphere sailors didn't have a convenient pole star. The star closest to the South Celestial Pole is Sigma Octantis, but it's faint, barely visible to the naked eye, even under ideal conditions. Not useful for navigation. So Southern Hemisphere navigators had to be more creative. They used constellations. The Southern Cross Crux became one of the most important navigational tools. The long axis of the cross points roughly toward the South Celestial Pole. It's not as precise as Polaris, but it works. Indigenous Australians used the Southern Cross for navigation for tens of thousands of years. The Maori of New Zealand called it Te Punga, the anchor, and used it to navigate the Pacific. European explorers arriving in the Southern Hemisphere adopted the same technique, relying on a constellation that had guided other cultures long before they arrived. But stars don't just tell you direction. They also tell you latitude, how far north or south you are. Here's how it works. The angle between Polaris and the horizon is equal to your latitude. If Polaris is directly overhead, you're at the North Pole 90 degrees north latitude. If Polaris sits on the horizon, you're at the equator 0 degrees latitude. If it's halfway between the horizon and directly overhead, you're at 45 degrees north. Sailors used instruments called astrolabes and later sextants to measure this angle with precision. By measuring the altitude of Polaris, they could determine their latitude to within a degree or so. That's accurate enough to navigate coastlines, avoid hazards, find islands. But latitude is only half the problem. You also need longitude, how far east or west you are. And that's much harder. The Earth rotates 360 degrees in 24 hours, which means it rotates 15 degrees per hour. If you know the exact time at a reference location, say Greenwich, England, and you compare it to the local time where you are, you can calculate your longitude. But how do you know the exact time in two places at once when you're on a ship in the middle of the ocean? For centuries, this was one of the greatest unsolved problems in navigation. Sailors could determine latitude easily enough, but longitude was a guess. Ships would sail to the correct latitude and then head east or west until they hit land. It worked, but it was slow and dangerous. Then in the 18th century, a clockmaker named John Harrison built a series of marine chronometers, clocks accurate enough to keep time on a rolling ship for months at a time. If you carried a clock set to Greenwich time and compared it to local solar time, you could calculate longitude. This revolutionized navigation. Suddenly, ships could pinpoint their position anywhere on Earth. Trade routes became faster. Exploration became safer. The world became smaller. But before chronometers, before precise clocks that could survive sea voyages, astronomers tried another approach, using the sky itself as a clock. Galileo Galilei, in the early 1600s, discovered that Jupiter has 4 large moons: Io, Europa, Ganymede, and Callisto. These moons orbit Jupiter with clockwork regularity. Io completes an orbit in about 42.5 hours. Europa takes about 85 hours. Ganymede, about 172 hours. Callisto, about 400 hours. Galileo realized that if you could predict where these moons would be at any given time, you could use them as a celestial clock. If you observed the moons through a telescope and compared their positions to a table of predictions calculated for a reference location, you could determine your longitude. It worked, in theory, but it required a telescope, a steady hand, and clear skies. On a rocking ship, it was nearly impossible. On land, those surveyors and explorers used Jupiter's moons to map coastlines and determine the size of continents with surprising accuracy. The sky became a timepiece. Not metaphorically, literally. The motion of celestial bodies was so regular, so predictable, that it could be used to measure time and location with precision. But humans weren't the only ones solving the navigation problem. Birds have been doing it for millions of years. Every year, billions of birds migrate thousands of miles. Arctic terns, for example, migrate from the Arctic to the Antarctic, and back a round trip of about 44,000 miles. That's nearly twice the circumference of the Earth. They do this every year, for their entire lives. How does a bird with a brain the size of a walnut navigate across oceans and continents without getting lost? Research suggests they use multiple cues: the sun's position during the day, the stars at night, the Earth's magnetic field, polarized light patterns in the sky, landmarks, even smell in some species. But the stars are a major part of it. Studies have shown that many migratory birds use the rotation of the night sky to orient themselves. They don't memorize individual stars, but they learn the pattern of rotation, the way the sky turns around the celestial pole. Young birds raised in planetariums where researchers could manipulate the artificial sky learned to navigate based on whatever star pattern they were shown. If the artificial sky rotated around a different star, the birds used that star as their reference point. It's learned behavior, not instinct. But it's learned early, and once learned, it lasts a lifetime. Some birds, like indigo buntings, migrate at night. They fly under the stars using the sky as a map. During the day, they rest. At dusk, as the first stars appear, they orient themselves and begin flying again. It's not perfect. Birds get lost. They're blown off course by storms. They make mistakes. But over millions of years of evolution, the ones who could navigate by starlight survived. The ones who couldn't didn't make it home. And now, billions of birds carry that knowledge in their genes and their learned behaviors, crossing hemispheres, following routes. Their ancestors flew, guided by the same stars humans once used to cross the same skies. Sea turtles do something similar. Loggerhead sea turtles, born on beaches in places like Florida, crawl into the ocean as hatchlings and disappear into the Atlantic. They spend years drifting in ocean currents, feeding, growing. Then when they reach maturity, sometimes 20 or 30 years later, they return. Not just to the same coastline, not just to the same beach, but often to the exact stretch of sand where they hatched. How research suggests they use Earth's magnetic field as a map. But they also use the stars. Studies have shown that hatchlings use the brightest part of the night sky, usually over the ocean, to orient themselves as they crawl toward the water. If you block their view of the sky, they become disoriented. The sky guides them from the first moments of life, and it continues to guide them for decades across thousands of miles of open ocean until they return to where they began. Even insects navigate by starlight. Dung beetles. Yes, dung beetles. Roll balls of dung across the ground at night. They need to move in a straight line away from the dung pile where competition is fierce to bury their prize. Scientists discovered that on moonless nights, dung beetles navigate using the Milky Way. They don't identify individual stars. They use the diffuse glow of our galaxy as a reference, keeping it at a constant angle as they roll their dung balls in a straight line. When researchers put tiny hats on dung beetles, actual tiny hats that blocked their view of the sky, the beetles wandered in circles, removed the hats, and they immediately corrected course. It's not intelligence in the way we usually think of it. It's something else. A sensitivity to light, a simple rule, encoded in a nervous system. Keep that glow at the same angle, and you'll move straight. But it works. It's enough. Evolution doesn't demand perfection, only survival. And the night sky provides enough information for creatures of all sizes, from birds crossing continents to beetles rolling dung to find their way. Humans, though, humans turn celestial navigation into an art form. We didn't just follow the stars. We mapped them, we named them. We built instruments to measure them with ever-increasing precision. Vikings sailing the North Atlantic 1,000 years ago navigated using a tool called a sunstone. These were crystals, likely calcite or cordierite, that have unusual optical properties. When you look through certain crystals at the sky, even on a cloudy day, you can detect the polarization of sunlight and determine where the sun is, even if you can't see it directly. Research has confirmed that this technique works. Even under heavy cloud cover, a skilled navigator with a sunstone can find the sun's position and use it to determine direction. The Vikings used this combined with their knowledge of the stars and ocean currents to cross the Atlantic, reaching Iceland, Greenland, and eventually North America, centuries before Columbus. Arab navigators crossing the Indian Ocean developed a tool called a kamal, a simple wooden board with a string attached. By holding the string in your teeth and positioning the board so that one edge aligned with the horizon and the other with a known star, you could measure the star's altitude. Different knots in the string corresponded to different latitudes. It's elegant, portable, effective, and it allowed Arab traders to navigate thousands of miles of open ocean, establishing trade routes that connected East Africa, the Middle East, India, and Southeast Asia. Chinese sailors used star charts drawn on paper or silk, showing the positions of stars at different latitudes. These charts, combined with compasses and detailed knowledge of winds and currents, allowed them to navigate across the South China Sea and into the Indian Ocean. Every culture that ventured onto open water developed some method of celestial navigation. The techniques varied, but the principle was the same: the sky is reliable. The stars don't lie. If you watch them carefully, if you learn their patterns, they'll tell you where you are and where you're going. And they still do. Even today, when GPS satellites can pinpoint your location to within a few feet, celestial navigation is still taught. The U.S. Naval Academy still requires midshipmen to learn how to navigate by stars. Because satellites can fail, electronics can malfunction, but the stars are always there. As long as the sky is clear, as long as you know what you're looking at, you can find your way. There's something profound in that, something reassuring. The universe, for all its vastness and strangeness, is also predictable, reliable, knowable. The stars move in patterns we can learn. The Earth rotates at a constant rate. Physics doesn't change based on where you are or who you are. The same laws that govern the stars also govern your position on this planet. And that means you're not lost. Not really, not as long as you can see the sky. You're part of a system, a vast cosmic system that extends from the ground beneath your feet to the farthest galaxies. And within that system, there are rules, patterns, regularities. The stars aren't just beautiful, they're functional. They're tools. They're maps written in light clocks that never stop ticking, guides that never sleep. And for thousands of years, humans and birds and turtles and even beetles have looked up and found their way home. The night sky is a gift, not a metaphorical gift, a practical one. A map that never fades, a compass that never breaks, a clock that never needs winding. All you have to do is look up, pay attention, remember. The stars will do the rest. They've been guiding travelers since the first creature looked up and wondered. They'll keep guiding travelers long after we're gone, because the sky doesn't belong to us. We just learned to read it, and in reading it, we found our place in the world. We found our way across oceans and deserts and continents. We found each other, all because we looked up, and the stars looked back. But the stars don't just guide travelers across earthly distances. Between the points of light in the vast spaces we once thought empty, there's something else, something most of us never see, but something essential to the story the night sky tells. That essential something hiding in the spaces we thought were void turns out to be where everything begins. The darkness between stars isn't empty. It's pregnant with possibility, with the raw material of creation, with clouds of gas and dust so vast they dwarf entire solar systems, yet so diffuse you could pass through them and barely notice. The space between stars is where stars are born, and death too, because the dust and gas filling the void aren't random. They're the remnants of stars that lived and died long ago. They're atoms scattered across light years, waiting to collapse and ignite again. The universe recycles everything. Nothing is wasted, not even emptiness. When you look at the night sky, the darkness between the points of light seems like nothing, a background, a canvas for the stars to shine against. But it's not nothing. It's full, fuller than most of the universe, in fact. The average density of the universe is incredibly low. Scientists estimate there are only about 5 to 6 atoms per cubic meter of space on average. That's almost perfect vacuum. For comparison, the air you're breathing right now contains about 10 to the power of 25 atoms per cubic meter. The difference is incomprehensible, but in certain regions of space and the vast clouds drifting between stars, the density is higher, much higher. These clouds, called nebulae, contain hydrogen, helium, and traces of heavier elements. They're cold, typically only a few degrees above absolute zero, and they're enormous. Some nebulae span hundreds of light years. These clouds are the places where stars form, and they're everywhere. One of the most famous is the Orion Nebula, located about 344 light years from Earth. On a clear night, if you look at the Sword of Orion, the 3 stars hanging below the belt, the middle star looks fuzzy. That's not a star. It's the Orion Nebula, a massive cloud of gas and dust where thousands of new stars are being born. The Orion Nebula is what astronomers call a stellar nursery. Inside the cloud, gravity is slowly pulling gas and dust together. As material accumulates, it heats up. Pressure builds. Eventually, if enough mass gathers in one place, the core becomes hot and dense enough for nuclear fusion to begin. Hydrogen atoms fuse into helium, releasing enormous amounts of energy. A star is born. This process takes millions of years. We don't see individual stars form in real time, But we can see different stages of the process happening in different parts of the nebula. Some regions are just beginning to collapse. Others already contain young hot stars that have ignited and are now blasting the surrounding gas with radiation and stellar winds. The Orion Nebula glows because of these young stars. Their ultraviolet light ionizes the hydrogen in the cloud, causing it to emit visible light, primarily red and green wavelengths. That's what gives nebulae their characteristic colors in photographs. But here's the thing, the colors you see in most nebula images aren't quite what you'd see with your eyes. Nebulae are faint, really faint. If you looked at the Orion Nebula through a telescope, you'd see a pale grayish glow. The vivid reds and blues and purples in Hubble images come from long exposures and filters that isolate specific wavelengths. It's not fake, it's enhanced, revealing details and structures that are really there, but too dim or too specific to certain wavelengths for our eyes to perceive. And what those images reveal is extraordinary. The Orion Nebula contains structures called proplids, protoplanetary disks. These are swirling disks of gas and dust surrounding young stars. It's in these disks that planets form. We can't watch planets form. It takes millions of years. But we can see the disks. We can measure their size, their mass, their composition. And we can infer what's happening inside them. Dust grains stick together. Pebbles form. Pebbles collide and merge into boulders. Boulders grow into planetesimals. Planetesimals sweep up more material, growing into protoplanets. Eventually, if everything goes right, you get a planetary system like ours. Our solar system formed this way about 4.6 billion years ago. We weren't there to see it, of course, but we can see similar processes happening in nebulae like Orion. We're watching the birth of solar systems that might billions of years from now host planets where something might look up at their own night sky and wonder. But not all nebulae are stellar nurseries. Some are the opposite stellar graveyards. When a star like our Sun reaches the end of its life, it swells into a red giant, then sheds its outer layers into space. What's left is a hot, dense core called a white dwarf, surrounded by an expanding shell of gas. This shell is called a planetary nebula, a misleading name since it has nothing to do with planets. Early astronomers thought they looked like planets through their telescopes, and the name stuck. Planetary nebulae are beautiful. They come in all kinds of shapes: spheres, rings, butterflies, hourglasses. The shapes depend on factors like rotation magnetic fields and whether the star had a companion. One of the most famous is the Ring Nebula in the constellation Lyra. It looks like a glowing donut in the sky. The white dwarf at the center is still hot enough to ionize the gas, making it glow, but the dwarf is cooling. Over billions of years, it will fade, becoming a cold, dark cinder. And the nebula will disperse its atoms, mixing with the interstellar medium, eventually becoming part of the next generation of stars. This is how the universe enriches itself. The first stars formed shortly after the Big Bang contained only hydrogen and helium, the lightest elements. Everything heavier than helium is made inside stars through nuclear fusion: carbon, oxygen, nitrogen, iron. All the elements that make up planets and life, they're all forged in stellar cores. And when stars die, they return those elements to space. Supernova explosions scatter them across light years. Planetary nebulae release them gently. Either way, the atoms that were once inside a star become part of the interstellar medium. The next generation of stars forms from gas enriched with these heavier elements. Planets form from the leftovers. Life, if it arises, is built from atoms that were cooked inside the cores of ancient stars. Carl Sagan famously said, "We are made of star stuff." It's not poetry, it's literal. Every atom in your body, except for hydrogen, which was made in the Big Bang, was created inside a star that died before our solar system even existed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in stellar furnaces scattered into space and eventually gathered into the cloud of gas and dust that became our sun, our planets, and us. You are the universe rearranged. But the interstellar medium isn't just gas, there's also dust. Tiny solid particles typically less than a micrometer across, made of carbon, silicon, and other heavy elements. These dust grains are important. They provide surfaces where molecules can form. In the cold depths of interstellar clouds, hydrogen atoms meet on the surface of dust grains and bond together, forming molecular hydrogen. Other molecules form too: water, carbon monoxide, ammonia, even complex organic molecules like formaldehyde and ethanol. Yes, there's alcohol in space, vast clouds of it. In 2006, astronomers discovered a cloud near the constellation Aquila that contains enough ethanol to fill 400 trillion pints of beer. Not that you'd want to drink it, it's mixed with a lot of other chemicals and it's spread across hundreds of light years. But it's there. The point is, space is chemically active. In the darkness between stars and clouds so cold and diffuse they seem like nothing, molecules are forming. Chemistry is happening. The building blocks of life are assembling. Some scientists suggest that complex organic molecules formed in interstellar clouds might have been delivered to the early Earth by comets and meteorites, jump-starting the chemistry that led to life. It's speculative, but the fact that complex molecules exist in space at all is remarkable. The darkness isn't sterile, it's creative. It's building molecules, forming dust, collapsing into stars, spinning into planets, all in the space we thought was empty. But dust has another effect: it blocks light. If you look at photographs of the Milky Way, you'll see dark lanes and patches cutting through the bright band of stars. These aren't gaps where there are no stars. They're regions where dust clouds block the light from stars behind them. These are called dark nebulae. The most famous is probably the Horsehead Nebula in Orion, a dark silhouette shaped vaguely like a horse's head, backlit by glowing hydrogen gas. The dust in the nebula is so thick that it absorbs almost all visible light. Stars behind it are completely hidden. But remember, dust that blocks visible light is often transparent to infrared. So if you observe the same region in infrared, the dark nebula becomes transparent and you can see the stars behind it. You can even see protostars forming inside the cloud, glowing in infrared. As they gather mass and heat up, not yet hot enough to ignite fusion, but already radiating energy. Dust shapes what we see. It obscures some parts of the galaxy and reveals others. It reddens starlight, scattering blue wavelengths and letting red wavelengths pass through the same reason sunsets are red. Light from distant stars passes through dust clouds, and by the time it reaches us, it's shifted toward red. Astronomers have to account for this. They measure the amount of reddening and correct for it, estimating how much dust lies between us and the stars we're observing. It's detective work, using light to infer the presence of something that's trying to hide the light. The center of our galaxy, as we mentioned earlier, is hidden behind thick clouds of dust. In visible light, we can't see it. But the dust is there for a reason. The galactic center is dense with gas, and dust a region of intense star formation and violent activity. At the very center sits Sagittarius Ace, the supermassive black hole. Surrounding it are massive stars, some of the largest in the galaxy, living fast and dying young. There are vast clouds of gas heated to millions of degrees by shock waves from supernova explosions. There are magnetic fields so strong they accelerate particles to near the speed of light. It's chaos, beautiful, violent chaos. And we can't see most of it in visible light because the dust is in the way. But in infrared radio waves and X-rays, we can see through the dust. We can map the structure of the galactic center. We can watch stars orbit the black hole, their motions revealing its mass. We can trace the flow of gas as it spirals inward, feeding the black hole and triggering bursts of radiation. The darkness reveals as much as it hides. You just have to know how to look. There's a certain kind of nebula that astronomers find particularly interesting: molecular clouds. These are the densest, coldest nebulae where hydrogen exists not as individual atoms, but as molecules H2. Molecular clouds are where the most massive stars form. One of the largest molecular clouds near us is the Taurus molecular cloud, about 430 light-years away. It's vast, spanning over 30 light-years, and contains enough material to make thousands of stars. Inside the cloud, gravity is pulling material into dense cores. Some of these cores will collapse and ignite, becoming stars. Others won't gather enough mass and will disperse. Star formation is inefficient. Only a small fraction of the gas in a molecular cloud actually becomes stars. The rest is blown away by stellar winds and radiation from the young stars that do form. These winds and radiation also prevent nearby regions from collapsing, shutting down star formation in the surrounding area. It's a self-limiting process. Stars prevent more stars from forming nearby. But on larger scales across the galaxy, star formation continues. New molecular clouds form from gas enriched by previous generations of stars. The cycle repeats, and this cycle has been repeating for billions of years. Our galaxy, the Milky Way, is about 13.6 billion years old, almost as old as the universe itself. It has gone through countless generations of star formation. The oldest stars in the galaxy contain very few heavy elements because they formed early when the universe was still mostly hydrogen and helium. Younger stars like our Sun are richer in heavy elements because they formed from gas enriched by earlier generations. Astronomers can measure the composition of stars and use it to estimate their age. It's not precise, but it gives a sense of when a star formed and what the galaxy looked like at that time. And what they've found is this star formation has been declining. The Milky Way formed stars much more rapidly in the past than it does now. The gas is running out. Most of it has already been turned into stars or locked up in planets, brown dwarfs, and other objects that don't shine. The universe is slowly running down. Entropy is winning. In the far future, trillions of years from now, star formation will cease entirely. The last stars will burn out. The universe will go dark. But we're not there yet. Not even close. Right now, the universe is still full of nebulae, still forming stars, still creating planets. The darkness between stars is still alive with potential. And when you look up at the night sky, remember the darkness isn't empty. It's full of gas and dust and complex molecules, full of collapsing clouds and igniting protostars, full of the raw material that makes everything stars, planets, and us. The void is a womb. The darkness is creative. And the space between the stars is where the future is being born. Every atom in your body was once part of that darkness, drifting in a cloud, waiting. And somehow, through the slow, patient work of gravity and chemistry and time, those atoms came together. They formed a planet. They became part of life. They became you, and one day they'll return to the darkness. Your atoms will disperse. They'll join the interstellar medium. They'll become part of the next generation of stars and planets. Nothing is lost. Everything is transformed. The universe doesn't end. It recycles, over and over, forever. The darkness isn't death. It's the pause between breaths, the silence between notes, the space where something new can begin. And in that space, in the cold, quiet dark between the stars, the universe is dreaming. Dreaming of what it will become next. Dreaming in hydrogen and helium and stardust. Dreaming in light, waiting to be born. But not all light is born quietly in the gradual collapse of cold clouds. Sometimes the universe creates light through violence, through explosions so powerful they briefly outshine entire galaxies, through cosmic catastrophes that tear stars apart and scatter their atoms across the void. Those catastrophes, those moments of cosmic violence, happen in silence. No sound, no shockwave that reaches us. Just light. Pure ancient light, carrying news of destruction across distances so vast that by the time we see it, the event is long over. The star is already gone. The explosion has already faded, and we're just now receiving the message. The universe destroys with grace, with beauty, with a kind of violence so enormous it becomes almost peaceful. Because what we call destruction is also creation. Every explosion seeds the cosmos with new elements. Every death makes new life possible. The violence isn't meaningless, it's necessary. And when you see a streak of light across the night sky, a shooting star, a meteor, you're witnessing the gentlest version of that violence. A tiny fragment of cosmic debris, no bigger than a grain of sand burning up as it enters Earth's atmosphere. It's not a star falling, it's a farewell. A small piece of the universe saying goodbye. On any clear night, if you watch the sky long enough, you'll see one. A brief flash, a line of light that appears and vanishes in less than a second. We call them shooting stars, but they're not stars at all. They're meteors, fragments of rock or metal, usually left behind by comets traveling through space at tens of thousands of miles per hour. When these fragments hit Earth's atmosphere, friction heats them to thousands of degrees. The air around them glows. The meteor itself usually vaporizes, completely never reaching the ground. What you see is the light of its destruction, the final moments of something that might have been drifting through space for millions of years. Most meteors are tiny, pebble-sized or smaller, but occasionally Earth passes through a particularly dense stream of debris and we get a meteor shower. Dozens or even hundreds of meteors per hour, all appearing to radiate from the same point in the sky. The Perseids visible every August are one of the most reliable meteor showers. They occur when Earth passes through the debris trail left by comet Swift-Tuttle, which orbits the Sun once every 133 years. The comet sheds material. As it approaches the Sun, ice vaporizes, releasing dust and rock. That debris spreads out along the comet's orbit, and every year Earth crosses that orbit, sweeping up the fragments. The meteors all seem to come from the constellation and Perseus, hence the name. But that's an illusion of perspective. The debris is spread throughout a large region of space. It's just that, from our point of view on Earth, the meteors' parallel paths make them appear to originate from a single point. It's the same effect you get when you drive through falling snow. The snowflakes seem to radiate outward from a point in front of you, even though they're actually falling straight down. Perspective creates the pattern. The Geminids in December are another spectacular shower. They're unusual because they come from an asteroid, not a comet. The asteroid is called 3200 Phaethon, and scientists aren't entirely sure why it sheds so much debris. Asteroids don't usually leave trails like comets do, but Phaethon does. Every December, Earth passes through that trail, and the sky fills with meteors. On a good night during the peak of a meteor shower, you might see one meteor every minute or two. It's not constant. You have to be patient. You have to let your eyes adjust to the darkness, find a spot away from city lights, and just watch. But when you do see one, when a line of light suddenly appears, streaks across the sky, and vanishes, there's something deeply satisfying about it. Something primal. For a moment, you're connected to a piece of the cosmos, a fragment that might have been drifting in space since before you were born, finally meeting Earth's atmosphere, finally burning up, finally becoming light. Most meteors never touch the ground, but some do. If a meteor is large enough, it can survive the journey through the atmosphere and impact the surface. When that happens, it's called a meteorite. Meteorites are rare. Most meteor showers produce nothing but vapor and light. But occasionally a larger object makes it through. Scientists study meteorites carefully because they're samples of the solar system, pieces of asteroids, fragments of planets that never fully formed, remnants from the early days of the solar system, 4.6 billion years ago. Some meteorites contain organic molecules, complex carbon compounds that are the building blocks of life. Some contain water. A few even contain amino acids, the molecules that make up proteins. This has led some scientists to suggest that life on Earth might have been jump-started by material delivered from space. It's called panspermia, the idea that the ingredients for life, or even life itself, might have originated elsewhere and been transported to Earth by comets and meteorites. It's speculative. We don't know for sure, but the fact that organic molecules exist in meteorites is remarkable. It means chemistry was happening in the early solar system. Complex chemistry, the kind that under the right conditions might lead to life. Every meteor you see is a reminder that Earth is not isolated. We're constantly being bombarded by material from space. Most of it is harmless dust and pebbles that burn up in the atmosphere, but occasionally something larger hits. About 66 million years ago, an asteroid roughly 6 miles across struck Earth near what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs. It vaporized rock, created a crater over 100 miles wide, triggered earthquakes and tsunamis, and threw so much debris into the atmosphere that the sky darkened for months. The impact caused mass extinction. About 75% of all species on Earth died, including the non-avian dinosaurs. The world that existed before the impact was gone. The world that emerged afterward was different. And in that new world, mammals, small, adaptable creatures that had been living in the shadows of the dinosaurs, began to thrive. If that asteroid hadn't hit, would humans exist? Probably not. Not as we are. Evolution would have taken a different path. The dinosaurs might still dominate, or something else entirely might have evolved. The point is, cosmic violence shapes life, not just by creating the elements we're made of, but by changing the conditions on planets, by clearing the stage for new actors, by forcing evolution to adapt or die. The universe is not gentle, but its violence is not random. It's part of the process, part of the way complexity emerges from chaos. But meteors are the gentle end of cosmic violence. Let's talk about the other end, the truly catastrophic, the kind of violence that makes asteroid impacts look like whispers. Let's talk about supernovae. A supernova is the explosion of a star, not a small star, not a gradual death, but a massive star, at least 8 times the mass of the sun, reaching the end of its life and detonating with so much energy that for a few weeks it can outshine an entire galaxy of billions of stars. Here's how it happens. Massive stars burn through their fuel much faster than smaller stars like our sun. Our sun will live for about 10 billion years. A star with 20 times the sun's mass might live for only 10 million years. It burns hot, burns fast, and runs out of fuel quickly. As the star burns, it fuses hydrogen into helium in its core. When the hydrogen is exhausted, the core contracts and heats up until it's hot enough to fuse helium into carbon and oxygen. When the helium runs out, the core contracts, again fusing carbon into heavier elements. This process continues neon, magnesium, silicon, each stage lasting a shorter time than the last. Finally, the core is fusing silicon into iron, and then it stops, because iron is different. Fusing iron doesn't release energy. It absorbs energy. Once a star's core turns to iron, fusion can't continue. There's no more fuel, no more outward pressure to balance the inward pull of gravity. And so, the core collapses. In less than a second, a core the size of Earth collapses to a sphere about 10 miles across. The density becomes unimaginable. Protons and electrons are crushed together, forming neutrons. What's left is a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain. But the collapse doesn't stop cleanly. The infalling material rebounds off the ultra-dense core. A shockwave blasts outward, ripping the star apart. The outer layers are blown into space at speeds of up to 10% the speed of light. The explosion releases more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. That's a supernova. The light from a supernova can be visible across the galaxy. In 1054, as we mentioned earlier, Chinese astronomers recorded a guest star that appeared in the sky and was bright enough to be seen during the day. That was a supernova. The remnant is now the Crab Nebula, still expanding, still glowing from the energy of that ancient explosion. In 1604, a supernova appeared in the constellation Ophiuchus. It was visible to the naked eye for over a year. astronomers across Europe, including Johannes Kepler, observed it carefully. It's now called Kepler's supernova, the last supernova visible to the naked eye in our galaxy. But supernovae don't just create light, they create elements. Remember, fusion inside stars can only produce elements up to iron. Everything heavier than iron, gold, silver, uranium, lead is made in supernovae. The intense energies and neutron-rich environment of the explosion allow rapid nuclear reactions that create heavy elements. So, when you wear a gold ring, you're wearing atoms that were forged in a supernova explosion. When you use a lead pencil, you're holding material created in the death of a star. The heavy elements that make up planets, that make up technology, that make up parts of your body, they all came from supernovae. Carl Sagan said we are made of star stuff. More specifically, we are made of supernova stuff. The violent deaths of massive stars scattered the elements needed for planets and life across the galaxy. Without supernovae, we wouldn't exist. The paradox is almost poetic. Destruction creates. Death enables life. The most violent events in the universe are also the most essential. But there's an even more violent kind of supernova. It's called a Type Ia supernova, and it happens in a completely different way. A Type Ia supernova occurs in a binary star system, two stars orbiting each other. One of the stars is a white dwarf, the remnant of a sun-like star that has already shed its outer layers and stopped fusing elements. The other star is still active, still burning. If the stars are close enough, the white dwarf can pull material from its companion. Slowly, the white dwarf gains mass. And white dwarfs have a limit about 1.4 times the mass of the Sun, called the Chandrasekhar limit. If a white dwarf exceeds this mass, it becomes unstable, and then it explodes. All at once, the entire star detonates in a runaway fusion reaction. Carbon and oxygen fuse into heavier elements, releasing so much energy that the white dwarf is completely destroyed. Nothing is left. Not even a neutron star or black hole. Just an expanding cloud of debris. Type Ia supernovae are important to astronomers because they're remarkably consistent. Every Type Ia supernova has roughly the same brightness at peak, about 5 billion times brighter than the Sun. This makes them useful as standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it is. In the 1990s, astronomers used Type Ia supernovae to measure distances to galaxies billions of light years away. And what they found was shocking. The expansion of the universe is accelerating. Distant galaxies aren't just moving away from us, they're moving away faster and faster. This discovery led to the concept of dark energy, a mysterious force that seems to be pushing the universe apart. We don't know what dark energy is. We just know it exists because of the observations of distant supernovae. Violence, even in its most extreme forms, teaches us about the universe. But there's one more kind of cosmic violence worth mentioning. Something even more extreme than a supernova. Something so energetic that if it happened too close to Earth, it could end life on our planet. Gamma-ray bursts. Gamma-ray bursts, or GRBs, are the most energetic events in the universe. They're brief, lasting anywhere from milliseconds to several minutes. But during that time, they release as much energy as the Sun will emit over its entire lifetime. Some release even more. Scientists believe GRBs are associated with the deaths of extremely massive stars, over 25 times the mass of the Sun. When these stars collapse, they don't just form a neutron star, they form a black hole. And in the process, they launch jets of gamma rays and particles at nearly the speed of light. If one of these jets is pointed toward Earth, we see a gamma ray burst. It's pure luck or unluck of geometry. The jet is narrow, only a few degrees wide. Most GRBs are pointed away from us, and we never see them, but the ones we do see are astonishing. The gamma rays themselves can't penetrate Earth's atmosphere, which is fortunate, but satellites orbiting above the atmosphere can detect them. And what they've found is that GRBs occur somewhere in the universe about once per day. Once per day, somewhere in the cosmos, A star is dying so violently that it sends a beam of energy across the universe bright enough to be seen billions of light years away. If a GRB occurred within a few thousand light years of Earth and was pointed in our direction, it could be catastrophic. The gamma rays would strip away the ozone layer, exposing the surface to deadly ultraviolet radiation. It could trigger a mass extinction. Some scientists have speculated that a nearby GRB might have been responsible for one of Earth's past mass extinctions, the Ordovician extinction about 450 million years ago. There's no proof, but it's possible. The good news is that GRBs are rare in our region of the galaxy. The stars massive enough to produce them don't last long, and there aren't many of them. The risk is low, not zero, but low. Still, it's a reminder, the universe is not safe. It's not designed for our comfort. It's wild, violent, unpredictable. And yet somehow in the midst of all that chaos, life found a way. We found a way. We exist in the brief, quiet moments between catastrophes, in the gaps between supernovae and gamma-ray bursts, in the sheltered corners of a galaxy where conditions are stable, calm enough for complex chemistry to become life. And that life, us looks up at the sky and sees the evidence of ancient violence, the remnants of explosions, the scattered debris of dead stars, the light from events so powerful they defy comprehension. But we don't just see destruction, we see beauty, we see the process. We see the way the universe builds and rebuilds itself over and over through cycles of creation and destruction that have been running for 13.8 billion years. The violence isn't the end of the story, it's part of the story, a necessary chapter in the long, slow process of becoming. And when you see a meteor streak across the sky, or read about a supernova in a distant galaxy, or think about the gamma rays silently crossing the cosmos, remember, you're seeing the universe at work, tearing down, building up, transforming matter and energy into new forms, new structures, new possibilities. The universe doesn't rest, it doesn't stop, it just keeps going, creating and destroying, over and over, forever. And somewhere in that endless cycle, in the brief intervals of peace life, emerges, looks up, wonders. But there's one thing in the night sky that doesn't seem violent at all, something steady, something familiar, something that's been watching Earth since long before life began. And that quiet companion has shaped more than just the tides. That quiet companion, Earth's only natural satellite, has shaped more than coastlines and ocean currents. It has influenced evolution itself, the rhythms of life, the cycles of sleep and waking, the very biology of creatures who have never thought about the moon, but whose bodies remember its pull nonetheless. The moon doesn't just hang in the sky, it reaches down, it touches everything: water, earth, blood, sleep. And we feel it even when we don't realize it, even when we're inside, away from windows surrounded by artificial light. Something in us still knows the moon is there, something ancient, something that remembers when the moon was closer, brighter, when its influence was impossible to ignore. The moon is not a distant object. It's a partner, a companion on a journey through space that's lasted 4.5 billion years. And in all that time, it has never stopped shaping the world beneath it. Let's start with the most obvious influence: tides. If you've ever stood by the ocean, you've seen the tide come in and go out. Twice a day the water level rises, twice a day it falls. The rhythm is so predictable that tide tables can be printed months or years in advance. But what causes tides? The moon, specifically the moon's gravity. Gravity isn't just a force that holds things together, it also stretches things. The moon pulls on Earth, and because gravity gets weaker with distance, the side of Earth facing the moon experiences a slightly stronger pull than the center of the planet. The side facing away from the moon experiences a slightly weaker pull. This difference in gravitational force creates what's called a tidal bulge. The oceans on the side of Earth facing the moon bulge outward, pulled toward the moon. The oceans on the opposite side also bulge, pushed outward by the difference in force. As Earth rotates, different parts of the planet pass through these bulges, creating high tides. There are 2 high tides and 2 low tides each day because there are 2 bulges, one facing the moon, one facing away. But the sun also creates tides. The sun is much more massive than the moon, but it's also much farther away. The result is that the sun's tidal effect on Earth is about half as strong as the moon's. When the sun and moon align during a new moon or full moon, their tidal forces add together, creating especially high and low tides called spring tides. When the sun and moon are at right angles to each other during the first and third quarters of the moon, their forces partially cancel out, creating smaller tides called neaptides. This has been happening for billions of years, and life on Earth evolved in a world governed by these tidal rhythms. Many marine organisms synchronize their reproductive cycles with the tides. Certain species of coral spawn during specific phases of the moon. Grunion, a small fish found along the coast of California, lay their eggs on beaches during the highest spring tides. The eggs incubate in the sand, and 2 weeks later, when the next spring tide arrives, the waves wash the newly hatched fish back into the ocean. These creatures don't have calendars. They don't calculate lunar phases, but they respond to environmental cues, light levels, water pressure, hormonal signals that correspond to the moon's cycle. Evolution has wired them to time their lives to the moon. Humans too have rhythms that seem connected to the moon, but the evidence is more complicated. For thousands of years, people have believed that the full moon affects human behavior. The word lunacy comes from the Latin word for moon luna, reflecting the ancient belief that the full moon could drive people mad. Hospitals and police departments have long reported increases in emergency room visits and crime during full moons. But when scientists have carefully analyzed the data, they have found little to no correlation. Study after study has shown that emergency room admissions, crime rates, psychiatric episodes, and accidents don't actually increase during full moons. The belief persists because humans are good at noticing patterns that confirm our expectations and ignoring data that doesn't. It's called confirmation bias. If you expect strange things to happen during a full moon, you'll remember the strange things that do happen and forget the ordinary nights. But, and this is interesting, there is some evidence that the moon affects sleep. Not dramatically, not in a way that would explain werewolves or lunacy, but measurably. In 2013, a study published in Current Biology analyzed sleep data from 33 volunteers who had spent several nights in a sleep lab. The researchers didn't tell the participants they were studying lunar effects. They only analyzed the data years later, after the experiment was over, to avoid bias. What they found was subtle but consistent. Around the time of the full moon, participants took an average of 5 minutes longer to fall asleep. Their total sleep time decreased by about 20 minutes, and their deep sleep, the most restorative stage, decreased by about 30%. The participants were sleeping in a controlled environment with no windows, no view of the moon, yet their sleep patterns still correlated with the lunar cycle. Why? No one knows for sure. One possibility is that moonlight itself affects sleep even when you can't see it directly. Even behind curtains, even through closed eyelids, some light might reach the brain and influence circadian rhythms. Another possibility is evolutionary. For most of human history, the full moon was the brightest night of the month, bright enough to travel by, bright enough to hunt, bright enough that predators could hunt you. It might have been advantageous to sleep a little lighter, to be a little more alert when the moon was full. This is speculative, but intriguing. The idea that our bodies still respond to a rhythm that was vital to our ancestors, even though we no longer consciously need it. Other studies have found similar patterns. In 2021, researchers analyzed sleep data from indigenous communities in Argentina and college students in Seattle. Despite living in very different environments, one with minimal artificial light, one saturated with it, both groups showed the same pattern: people slept less and went to bed later in the days leading up to a full moon. The effect was stronger in the communities with less artificial light, but it was present in both, as if the moon's influence persists faintly even in the modern world. But the moon's influence goes deeper than sleep. It affects the entire planet in ways that have shaped the history of life on Earth. The moon stabilizes Earth's axial tilt. Earth's axis is tilted about 23.5 degrees relative to its orbit around the sun. This tilt is what gives us season summer when your hemisphere tilts toward the sun, winter when it tilts away. But that tilt isn't fixed. Over thousands of years, it wobbles slightly due to gravitational interactions with the sun and other planets. Without the moon, that wobble would be much more extreme. Computer models suggest that without the moon, Earth's tilt could vary by tens of degrees over relatively short time scales, geologically speaking. Such dramatic changes in tilt would cause extreme climate shifts. The poles could tilt toward the sun, melting ice caps, or tilt away, plunging the planet into prolonged ice ages. The climate would be unstable, chaotic, unpredictable. But the moon's gravity dampens that wobble. It keeps Earth's tilt relatively stable. And that stability is one reason why Earth has had a relatively stable climate for billions of years, stable enough for complex life to evolve. The moon is a stabilizer, a guardian. Without it, Earth might still have life. But it would be very different life adapted to a world of wild climate swings. The moon also slows Earth's rotation. Tidal forces don't just move water, they also create friction between the oceans and the seabed, between Earth's crust and its molten interior. That friction slows Earth's spin. Billions of years ago, when the moon was younger and closer, Earth rotated much faster. A day might have been only 10 or 12 hours long. But over time, tidal friction has slowed the rotation. Days have gotten longer, and they're still getting longer by about 1.7 milliseconds per century. At the same time, the moon is moving away from Earth. As Earth's rotation slows, angular momentum is transferred to the moon, pushing it into a slightly higher orbit. Currently, the moon is drifting away at about 3.8 centimeters per year. That might not sound like much, but over millions of years it adds up. The moon used to be much closer. When it first formed about 4.5 billion years ago, it might have been only 15,000 miles from Earth, compared to about 239,000 miles today. Back then, the moon would have appeared enormous in the sky, filling a huge portion of the horizon. Tides would have been hundreds of feet high, reshaping coastlines with every rise and fall. The day would have been much shorter. The world would have been unrecognizable. And in the far future, the moon will be even farther away. Tides will be weaker. Days will be longer. Eventually, billions of years from now, Earth will become tidally locked to the moon, just as the moon is already tidally locked to Earth. One side of Earth will always face the moon. A day will equal a month, both lasting about 47 current days. But don't worry. The sun will die long before that happens. In about 5 billion years, the sun will expand into a red giant, likely engulfing both Earth and the moon. The distant future is far away. For now, the moon is still close enough to create tides to light up the night, to influence sleep and rhythms and the lives of creatures who depend on its cycles. There's something deeply comforting about the moon's presence. It's not a star burning with nuclear fire. It's not a planet massive and distant. It's just rock. Dead cold rock orbiting Earth, because it's been orbiting Earth for as long as Earth has existed. But that rock is ours. It's the only other world humans have ever walked on. 12 people between 1969 and 1972 left footprints on the moon. Those footprints are still there. There's no wind on the moon to erase them, no rain, no weathering. They'll last for millions of years unless a micrometeorite happens to hit the exact spot. For millions of years, there will be marks on the moon that say someone was here. Someone came from Earth and walked on another world. That's extraordinary, not just as a technological achievement, but as a symbol. For all of human history, the moon was untouchable, a light in the sky, a source of myth and wonder. And then, in 1969, humans reached it. Neil Armstrong's first words as he stepped onto the lunar surface were, "That's one small step for man, one giant leap for mankind." He was right. It was a giant leap, not just physically, but psychologically. It expanded the boundaries of what's possible. And yet, the moon remains mysterious. We've walked on it, studied it, brought back samples. But we don't fully understand how it formed. The leading theory is the giant impact hypothesis about 4.5 billion years ago, a Mars-sized object called Theia collided with the early Earth. The impact was so violent it vaporized parts of both bodies. Debris from the collision coalesced in orbit around Earth, eventually forming the moon. This would explain why the moon's composition is similar to Earth's crust, but lacks a large iron core. The debris came mostly from the outer layers of both worlds, not the cores. But there are details that don't quite fit. Scientists are still refining the theory, running simulations, comparing lunar samples to Earth rocks, trying to understand exactly how our companion came to be. The moon is a witness. It's been watching Earth for 4.5 billion years. It was there when the first oceans formed, when the first life emerged, when plants colonized the land and animals crawled out of the sea. It watched the dinosaurs rise and fall. It watched ice ages come and go. It watched humans evolve, build civilizations, develop language, art, science. And it's still watching, quietly, steadily, rising and setting, waxing and waning, pulling on the oceans, pulling on us. There's a strange intimacy in that. The moon doesn't care about us. It's not sentient. It's just rock following the laws of physics. But it's been here the whole time, a constant presence in the sky, a companion on the long journey through space. And maybe that's why we feel such a connection to it. Why every culture has moon myths, moon gods, moon rituals. Why poets write about moonlight and lovers meet under it. Why we still look up even now, in a world full of artificial light and distractions, and feel something when we see the moon hanging in the sky. It's familiar. It's ours. It's the one part of the cosmos that feels close enough to touch, and in a way, it is touching us. Every moment, with gravity, with light, with the subtle influence it's had on life and evolution, and the rhythms we don't even notice until we stop and pay attention. The moon is a quiet companion, but it's always there, shaping the tides, stabilizing the planet, lighting the night, watching over a world that without it might be very different, or might not exist at all. But the moon is just one part of the night sky's story. There's something larger still, something that holds all the light, all the darkness, all the stories we've explored. And in the end, that vastness doesn't just surround us. It reflects us. It reflects us because we are not separate from it. We've never been separate. Every atom in your body, every thought in your mind, every breath you take, it all comes from the same place the stars come from. The same hydrogen that fuels the sun flows through your veins as part of water molecules. The same carbon that forms in stellar cores makes up your DNA. You are not observing the universe. You are the universe observing itself. And when you look up at the night sky, you're not looking at something distant and foreign. You're looking at home, at family, at the vast, ancient, ongoing process that made you possible. The night sky doesn't just tell stories. It is the story, and you're part of it. Think about it. Every photon that enters your eye tonight traveled across unimaginable distances just to reach you. It left a star years, centuries, or millions of years ago, crossed the emptiness of space, passed through Earth's atmosphere, and arrived at the exact moment you happen to be looking up. What are the odds? What are the chances that this particular arrangement of atoms, this specific consciousness, this one life would exist at the precise moment to receive that light? Astronomically small. And yet, here you are. The universe is full of improbable events. Stars forming from collapsing clouds. Planets coalescing from debris. Life emerging from chemistry. Consciousness arising from biology. You standing beneath a sky full of light, wondering what it all means. None of it was guaranteed. All of it was possible. And the night sky is the evidence. It's proof that improbable things happen. That order emerges from chaos. That complexity arises from simplicity given enough time and enough space. For thousands of years, humans have looked up and asked questions. Why are we here? Where did we come from? What's out there? And slowly, patiently, the night sky has been answering. Not in words, not in messages written across the stars, but in patterns, in light, in the way things move and change and repeat. We've learned to read those answers. We've learned that the universe is ancient 13.8 billion years old, that it's expanding, carrying galaxies away from each other at ever-increasing speeds, that it's full of structures we can see and dark matter we can't, that stars are born live and die scattering the elements that make new stars, new planets, new chances for life. We've learned that we're not the center. Earth isn't the center. The sun isn't the center. There is no center. Or rather, every point is the center because space itself is expanding everywhere at once. We've learned that we're small, unimaginably small in the context of the cosmos. Our entire planet could fit inside the sun 1,000,000 times over. The sun is one star among 100 billion in the Milky Way. The Milky Way is one galaxy among trillions in the observable universe. But here's the paradox, we're also unimaginably significant. Because as far as we know, we're the only part of the universe that knows the universe exists. We're the only part that looks up and wonders, that builds telescopes and writes equations and tells stories about the stars. The universe has been around for 13.8 billion years. For most of that time, it just existed. Stars formed and exploded. Galaxies collided. Black holes devoured matter. But there was no one to witness it, no one to understand it, no one to care. And then, on a small planet orbiting an ordinary star in an unremarkable galaxy, something happened. Chemistry became biology. Biology became consciousness. And consciousness looked up. For the first time in the history of the universe could see itself, could understand itself, could ask questions about itself. That's what you are. You're the universe's way of knowing it exists. And that's not a small thing. That's everything. Scientists sometimes talk about the Copernican principle, the idea that humans aren't special, that we don't occupy a privileged position in the cosmos. And in one sense, that's true. We're not at the center. We're not made of special materials. The laws of physics that apply here apply everywhere. But in another sense, we are special, not because the universe was designed for us, but because we're the part that woke up, the part that learned to see beyond our own eyes, to think beyond our own lifetimes, to care about things that will happen long after we're gone. We're the universe contemplating itself, and that's worth something. The night sky reminds us of this. It reminds us that we're connected to something larger, that the same forces that shaped galaxies also shaped us, that the light we see isn't just light, it's information, it's history. It's a gift from the past, delivered across the void, waiting for someone to receive it, and you're receiving it, right now. Every time you look up, have you ever wondered what it would be like if humans had never looked up, if we'd never noticed the stars, never tracked their movements, never asked questions about the lights in the sky? We wouldn't have calendars, we wouldn't have navigation, we wouldn't understand time or space or our place in the cosmos. We'd be confined to the surface of a single planet with no sense of the vastness beyond. But we did look up, and in looking, we changed. We learned, we grew. We became something more than just another species trying to survive. We became explorers, questioners, storytellers. And the night sky was our first teacher. Every ancient civilization that looked up at the stars and tried to make sense of them was doing science. They didn't have telescopes or spectrographs or equations, but they had curiosity and patience, and the willingness to observe, record, and pass knowledge to the next generation. The Babylonians tracked Venus for centuries, building a data set that let them predict its movements. The Egyptians aligned their pyramids with such precision that we still marvel at it today. The Polynesians navigated thousands of miles of ocean using nothing but stars and waves and the accumulated wisdom of their ancestors. These weren't primitive people stumbling in the dark. They were scientists, astronomers, navigators. They were people who looked at the night sky and saw not just beauty, but information, patterns, meaning. And they used that meaning to survive, to thrive, to cross oceans and build civilizations and ask deeper questions. We're still doing the same thing. We're still looking up, still asking questions, still trying to understand. But now we have tools, telescopes that can see to the edge of the observable universe, satellites that can detect wavelengths our eyes can't perceive, computers that can simulate the birth of galaxies and the death of stars. And what we've found is more extraordinary than any myth, any story, any ancient cosmology could have imagined. We've found that the universe is stranger, larger, older, and more wonderful than we thought. That it's full of things we don't understand: dark matter, dark energy, black holes, neutrons, stars, phenomena we're still discovering and trying to explain. But we're explaining them, slowly, piece by piece, generation by generation. We're learning the language of the cosmos, and the cosmos, it turns out, speaks in mathematics and light and the motion of things across unimaginable distances. The night sky is a book, and we're learning to read it. But here's the thing, the night sky is also fragile. At least our ability to see it is. Light pollution is erasing the stars. In most cities, you can see only a handful of the brightest stars. The Milky Way, that band of light that every human for thousands of generations could see, is now invisible to 80% of people in North America and Europe. We're losing the night sky, not because the stars are going out, but because we've surrounded ourselves with so much artificial light that we can't see them anymore. And in losing the night sky, we lose something essential, not just data, not just beauty, but connection. The sense that we're part of something larger. The reminder written in light that the universe is vast and ancient and full of wonders. Children growing up in cities today might never see the Milky Way, might never experience a truly dark sky, might never lie on their backs and watch meteors streak across the darkness, feeling that strange mix of smallness and wonder that comes from looking up. That's a loss. Not just for science, but for the human experience, for the sense of awe that has driven us to explore, to question, to reach beyond ourselves. But it's not too late. Dark sky preserves exist. Places where the night is still dark, where the stars still shine as they did for our ancestors. And more are being created as people recognize that the night sky is worth protecting because it matters. Not in a practical sense maybe, but in a deeper sense. In the sense that reminds us who we are and where we came from. That we're not alone, not isolated, not separate from the cosmos. We're part of it, made of it, connected to every star, every galaxy, every photon that crosses the void. And when you look up at the night sky, you're not just seeing light. You're seeing time. You're seeing distance. You're seeing the past and the future collapsed into a single moment of perception. You're seeing the universe as it was, as it is, as it will be, all at once. And somehow, in the midst of all that vastness, all that time, all that impossible distance, you're here, right now, looking up. That's not nothing. That's everything. The night sky doesn't need us. It was here long before we existed. It will be here long after we're gone. Stars will keep burning. Galaxies will keep colliding. Light will keep traveling across the void. But for this brief moment in cosmic history, there's someone here to see it, to understand it, to care, and that someone is you. So when you look up tonight or any night, remember, you're not just looking at the stars, you're looking at yourself, at your history, at the atoms that make you scattered across billions of years and trillions of miles, finally gathered into the shape of a person. who can look up and wonder. You are stardust, made of light, made of time, made of the same material as everything you see in the night sky. And the night sky, it's not distant, it's not separate, it's family. We've walked through so much tonight. Ancient eyes watching the sky, learning to navigate by stars. Photons traveling millions of years to reach us. Colors we can't see carrying messages in wavelengths beyond human vision. Cosmic violence meteors, supernovae, gamma-ray bursts tearing through space and creating the elements we're made of. The darkness between stars pregnant with gas and dust and the seeds of new worlds. The moon, our quiet companion, pulling tides and shaping life. All of it is part of the same story. The story of a universe that has been unfolding for 13.8 billion years. A story that's still being written. And you're a chapter in that story. A sentence, a word, a single letter perhaps. But you're part of it. The night sky holds all of this, all the history, all the light, all the stories written in darkness. And tonight, it's still there, waiting, patient, eternal. All you have to do is look up, sleep well, dream gently, and when you wake, the stars will still be there, shining in the darkness, telling their stories to anyone willing to listen. Thank you for drifting with us tonight, for letting curiosity guide you through the darkness, for remembering that the universe isn't something separate from you, it's something you're part of. There are more stories waiting, more nights to explore, more light traveling across the void, carrying messages we haven't yet decoded. So, rest now. Let the night hold you, and when you're ready, we'll wander together again into the quiet spaces where science becomes wonder, and wonder becomes understanding. Until then, good night. The sky remembers you, and it's waiting.